Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome everyone to lecture 3 of week 4 of Atoms to Materials. Today we're going to continue with statistical mechanics, and we're going to apply it to a case that can be solved analytically, which is a harmonic solid. Okay, as we've seen in last week, in week 3, if we make an approximation to the Hamiltonian and we assume that atoms don't displace much away, don't move far away from their equilibrium position, we can do a Taylor expansion, cut it at the second order, and solve the dynamics of the system analytically. Well, we're going to see that under those same approximations, we can actually do quite a bit of statistical mechanics and learn quite a bit about how solids behave. So let's get started. Let's do a little bit of review before we jump into the harmonic solid. What we learned this week is that statistical mechanics allows us to relate the microscopic world and the macroscopic world, and this relationship goes both ways. So given a macroscopic set of conditions, thermodynamic conditions, we can compute using statistical mechanics the probability of finding the system at a specific location. And that's what you see here in the first line of equations for all of these ensembles. But also, statistical mechanics provides us with a way of, if I know the system microscopically, I can do a microscopic calculation and compute a thermodynamic potential. That's what you see at the bottom. Okay, so just as an example, in the canonical ensemble under constant temperature conditions, we have that the probability is the Maxwell-Boltzmann distribution. So the probability of a microscopic state is e to the negative the energy of that state divided by kT. And also we learned that from the partition function z, which can be obtained with knowledge only of atomistic microscopic information, if we know the partition function, we can compute the Helmholtz free energy, as you see over there. So that allows us to connect to thermodynamics. Okay. So there's a few more results that I'd like to highlight about statistical mechanics that are going to be useful for the next few lectures. One of them is that in the canonical ensemble, from the definition of partition function that you see here, remember the partition function is a sum over all possible microscopic states of the Maxwell-Boltzmann weight. From that definition of partition function, we can compute the average energy of the system. So, as you know, the definition of average energy of a system is sum over all microscopic state of the energy of that system times the probability of that microscopic state. And what we're going to show, you're going to show in the homework assignment, is that can be calculated as the derivative of the log of the partition function with respect to beta. Okay, so I'm not going to demonstrate that. It's very short, 2 lines of algebra derivation. The other thing I want to bring up is another ensemble. It's called the grand canonical ensemble, and in this ensemble, energy and the number of particles, the number of atoms, is not fixed, but they are allowed to fluctuate. Volume is fixed though. So the system of interest is allowed to exchange energy with the surrounding medium, but also exchange particles. Okay, so it has a permeable membrane separating the two systems. So the bath sets up the temperature of the system. That's because of the energy exchange, and it also sets up what's called the chemical potential of the system, and that's what controls the number of particles. So there's a grand canonical partition function, just like the canonical partition function. And the only difference is that in the grand canonical partition function, you sum over all microscopic states with any number of atoms. Okay, so you sum over all microscopic states with 0 particles, and sum over all microscopic states of 1 particle and 2 particles and 3 particles and so on and so forth. And the weight that you put in the exponential is e to the negative beta energy minus mu times n. Okay, mu here, that's the chemical potential. Okay, so that's the grand canonical partition function. It applies to systems where the separation with the environment is permeable, and it allows atoms to move in. The same way as we can calculate the average energy from the canonical partition function, we can compute the number of atoms from the grand canonical partition function, simply taking derivatives with respect to mu. Okay, and also you will demonstrate this in the homework assignment. Okay, one more slide of background. Okay, so we've been talking about so far average quantities. Okay, we just talked about average energy and average number of particles. But fluctuations are also important in statistical mechanics. And here I'm showing you the definition of the fluctuation of a quantity A. Okay, it's the average of the deviation of A from its mean. And of course, I have to square that so I get a non-zero value. Okay, so now fluctuations of quantities of interest like energies or the number of particles or the volume are associated with second order response functions in statistical mechanics. That means that the fluctuations have a meaning. And for example, the specific heat, here's the definition of specific heat. Well, specific heat has to do with the fluctuations of the total energy, okay, or the Hamiltonian of the system, and their NVT conditions. Okay, so a system with a large specific heat will have large fluctuations of energy under constant temperature. Okay, so being at constant temperature means more than just having an average kinetic energy equal to the temperature. It means having the entire distribution, Maxwell-Boltzmann distribution. Compressibility is how hard it is to change the volume of a system. Okay, an incompressible system is a system that the pressure goes up very quickly if I try to change the volume. A very compressible system is a system where I can change the volume significantly without much pressure. So that's the definition, what you see on the left. On the right, you can see that the compressibility, beta here, is related to the fluctuations in volume. Okay, so if I have a system under constant pressure, okay, in contact with a system with a bath at constant pressure, the fluctuations in volume have to do with their compressibility. Very incompressible systems will fluctuate, the volume will fluctuate very little, and very compressible systems, their volumes will fluctuate very significantly. The other important thing that one can learn from these fluctuations, expressions of fluctuations, is that the fluctuations go down as the systems become bigger. Okay, so as the number of atoms, okay, of the system becomes bigger, the fluctuations go down, decrease with 1 over the square root of the number of atoms. And that means that in the thermodynamic limit of a very large number of particles, the different ensembles give the same predictions. Okay, whether I have the energy of the system is exactly constant, or the system is able to exchange energy with the environment, thermodynamically they will behave the same way. Same thing is true for pressure. Okay, now we're ready to jump into the harmonic solid. And if you remember from week 3, the way we treated the harmonic solid, the way we motivate it is that if I'm at low temperatures, I can then expand my potential energy around the equilibrium positions and stop this Taylor expansion at second order. Okay, so the total Hamiltonian has kinetic energy. It has the potential energy of the ground state, okay, where all the atoms are in their minimum energy positions. And then I have this second order term that has to do with the second derivatives, the curvatures of the potential energy in which the atoms move. What we learned is that I can build a matrix called the Hessian matrix, and I can diagonalize this matrix. And what I get by doing that is that I learned that I can describe the system as a set of decoupled, okay, of independent harmonic oscillators, okay. The frequencies of these harmonic oscillators are the eigenvalues of the Hessian matrix, and the atomic displacements that have to do that correspond to this set of independent harmonic oscillators are the eigenvectors of the Hessian matrix. But the bottom line is that the potential energy can be written in this way. And of course, for the Hamiltonian, I also have a sum over all states of the kinetic energy. Okay? So great. So the bottom line is I can write the dynamics of my system as a set of 3n independent harmonic oscillators. Now, from the equipartition of energy, the principle of equipartition of energy that we learned in the previous lecture, we know that each degree of freedom that appears in the Hamiltonian squared contributes 1/2 of kT of energy to the system. So in this case, I have the total energy of the system as a function of temperature will be the ground state, the value, the energy of the system in its ground state, plus the thermal energy. And the thermal energy is 2 times 3n, and 2 times 3n is the number of degrees of freedom you have. I have 3n positions and 3n momenta, and each of them contribute 1/2 kT. So that's the expression for the total energy of the system. It's the ground state energy plus 3n kT. And from this expression, I can compute the specific heat of the system. It's the derivative of energy with respect to temperature. And I find that the specific heat is 3nk, or 3 times the Boltzmann constant per degree of freedom. Okay. So classically, we predict that the specific heat for a set of n atoms is 3nk. So we have 3 times Boltzmann constant per atom. And if we go look at the experiments, what we find is what you see in this plot on the left. That was taken from the Ashcroft-Mermin book. And what we find is that this is the specific heat as a function of temperature for a bunch of noble gas solids. And what happens is that at low temperatures, the specific heat goes down to 0. And as you increase the temperature, the specific heats go up, and they kind of approach the classical limit as you increase the temperature. And that's a bit surprising, okay, because our result is the approximations that we've made is the classical mechanics and the harmonic approximation. So we're approximating, we are assuming that we can stop our expansion of the potential energy at the second order term. And that should work very well at low temperatures where the atoms don't move away from their equilibrium positions much. So the harmonic approximation should be very good. Now, one thing to consider is that because of the equipartition of energy, the specific heat that we predict, 3 times K per atom, is independent of anything. Okay, it's just depends on the number of atoms that you have in the system. It doesn't depend on the nature of the interactions or anything, because the equipartition of energy says that you have 1/2 kT of energy per degree of freedom that appears squared in the Hamiltonian, regardless of what the prefactor is. So regardless of the frequency of the oscillation, regardless of the mass or this effective spring constant of the interactions, we always have 3 times K for the specific heat. Now, so what error did we make? Okay, and what we'll see now is that the error that we make is not that it's the harmonic approximation, it's classical mechanics that breaks down at low temperatures. So let's consider now a very simple system. Let's consider a diatomic molecule, and here I'm showing the energy as a function of the interatomic distance of, let's say, a small interatomic diatomic molecules. So these molecules are the separation distance between the two atoms are vibrating, okay, around some equilibrium distance. So let's say I have a kinetic energy that's this big, okay? So what will happen is the distance between the two molecules will oscillate between those 2 points, okay? So my molecule will do this, back and forth, back and forth, back and forth. Now, what happens if I reduce the temperature, okay, reduce the kinetic energy in that bond? Well, the oscillations will be smaller, okay? And if I reduce it even more, it will be even smaller, okay? And that's okay. One interesting thing that you see is that if you imagine what the average separation is between these two atoms, you can see that because of the asymmetry of the potential, as I move down, the equilibrium distance moves to, as I decrease the temperature, the equilibrium distance moves to smaller and smaller distance. Okay, that's thermal expansion. Okay, but that's not what we're dealing with now. Now, imagine I continue removing the energy of the system all the way until I bring the system to 0 degrees Kelvin. So, if I have the system at 0 degrees Kelvin, classical mechanics will say that there's no kinetic energy, so these two molecules will stop vibrating. So, there will be standing still, not moving at all, and at the equilibrium bond distance will be the minimum of the potential energy. That's great with classical mechanics, but of course we know that that's incorrect quantum mechanically. Okay, Heisenberg says that you cannot know both the position and the velocity of these particles with infinite accuracy, and that's what we need to do in order to bring the system to 0 temperature in a classical way. And that's the problem, okay, that classical mechanics doesn't account for this. I can remove the energy all the way until I make the molecule stop, and that leads to this wrong description of the specific heat. So to correct that, we'll have to incorporate quantum effects, and that's what we'll do in the rest of this lecture and in the following lecture. These quantum effects, as we will learn, appear when kT is very small. Okay, when kT is small compared to the quantum potential energy that has to do with its frequency, then we're in the quantum regime. So if kT is small compared to the quantum of vibrational energy, we're in the quantum regime. If kT is large, then we're classical, and then that's okay. And you could see in the previous plot that the specific heat was well described classically at high enough temperatures. Okay, so what do we need to do to solve the quantum harmonic oscillator? Well, we have to start with quantum mechanics. So the first thing we do is write the Hamiltonian operator, just like we did in weeks 1 and 2. I'm going to do it. Remember that the system at low temperatures can be described as a set of 3n independent harmonic oscillators. So they're independent. That means that I can add them up. So I'm going to solve for one harmonic oscillator and then add them up. So the Hamiltonian has a kinetic energy term and a potential energy term. Okay, I write this quantum mechanically. Okay, remember the kinetic energy has to do with the second derivative of the wave function with respect to position. And then I solve the Schrödinger equation. Okay, we don't have the time to show the solution of this in the lecture, but if you go to any of the quantum mechanical books that I pointed in the first few weeks, you'll find this solution. What happens when you solve this problem quantum mechanically is that, as always, we have a family of solutions for the Schrödinger equation. We have a family of eigenvalues that represent the allowed energies, okay? And the allowed energies are like this. The energy sub n, okay, n is the quantum number, is h bar times omega, okay, times 1/2 plus n, okay? So n is the quantum number, takes the values 0, 1, 2, 3, and so on and so forth, all the way to infinity. Okay, so interestingly, the smallest energy that the quantum oscillator can have is 1/2 of h bar omega. Okay, if you remember from week 1, the square well had the same feature, that the minimum energy that you could have with an electron in the square well was not 0 because it couldn't stop. This is the same thing here. And it's interesting that the harmonic oscillator is the only quantum mechanical system where the energy levels are equispaced throughout the spectrum of possible energy. So every state is at h bar omega from the states right below and right above. Okay, so that's great. So we have the system, what this shows is, as I was saying before, the lowest possible energy of the system is h bar 1/2 of h bar omega, and that means that I cannot make the system stop vibrating completely. Okay, it will always move around a little bit. I cannot remove that little bit of extra energy. And remember, we call that energy that remains at 0 temperature 0 point energy. Okay, in this case it's 1/2 h bar omega. Now what remains to be done is to compute the partition function. And in quantum mechanics, as in classical mechanics, the partition function is computed by summing over all microscopic states of e to the negative beta, the energy of that state. Now we know my states are n, okay? Those are all the possibilities, all the possible states in which my harmonic oscillator can be is n equals 0, 1, 2, 3, 4, all the way to infinity. And I know that the energy of each state is h bar omega times 1/2 plus n. So I plug that in, okay? We're going to solve this equation in the next lecture. So you'll have to wait until the next lecture to see the end of the quantum harmonic oscillator. But the goal is to fix the problem that we encounter by using classical mechanics to describe harmonic solids. I'll see you next lecture. Thank you.